So we are almost done with reactions. Can you believe it with this part of the lecture module? Reaction after reaction after reaction. I warned you in the very beginning that it would do this. And we're still not finished with the carbonyl family. Woo! I told you, tons and tons are coming your way. And it's just our job to know and learn a mechanism and be able to apply that mechanism with all of the other molecules and reactions that might come your way. So what we've kind of need to talk about before the end of this part of the lecture module are two more functional groups. And we're going to be able to do both of these functional groups, I think, in this one video. And the first one is a carboxylic acid. And you're going to see very quickly why I think we can cover both of these functional groups at one time. So if we have a carboxylic acid, a C double bond OOH, well, will this give us a reaction? That's the question. And you're probably scratching your head and thinking, well, why not? It's going to give us a reaction, just how many? Well, that's okay. It does do reactions. Granted, it does do them. But I want you to think about where the OH group falls onto that nucleophilicity chart. So let's go back and take a look at the nucleophilicity chart. Here it is. And if you look toward the bottom of this chart, you're going to see the OH group that's way down here at the very bottom. What that means is that not too many things out there will take the place of OH. It's like some of the others. If you've got an OH group on you, well, you got it pretty good. So why do you go out and try to find something to replace that OH when you're almost to the Mr. or Mrs. America at the bottom? So not too many things actually will come in and take the place of an OH group. So because of that, you're probably thinking, well, if that's the case, it looks like the only thing that the NH2 would work. That's a group that could come in and replace the OH. But also that C triple bond C was on that list as well. Okay, well, that's a very good start. You're thinking in the right place. But here's the thing. These go forward. We'll do an example of like the amine just to kind of go through that mechanism once more to show you how that reaction happens. But you're also forgetting a huge, big component of organic chemistry. If I asked you to give me the name of the C double bond OOH, you would give me a carboxylic acid functional group. Ding, 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 ding. There's the problem. It's an acid. It's a carboxylic acid. So basically what this means is that I could react a lot of the bases with it. Doesn't really matter what type of base, but a base could react with the acid, and then all of a sudden we get a removal of a proton. Now, that's not really major. And that's sometimes why we just briefly mention it and we go on about our business, because the only thing that's happening here is that this organic is staying as the organic. We are just removing the proton in order to give us this negatively charged organic remnant, which is basically an anion at that point in time. So that reaction is out there. I can take a carboxylic acid and I can react it with a base like NaOH or KOH. And that base could remove the proton from the acid molecule, and we're left with just a negative charge. And actually, any base will work here, folks. Any base, which basically means that can accept a proton, that is the reaction that a carboxylic acid will do. So we're just going to briefly touch on it and say, listen, There's this whole nother set of reactions that are out there. It is a traditional acid-base reaction because if we can drive up the pKa and if we can make it go above a 4-ish, then we can get this carboxylic acid to spit off a proton and away it goes. This was kind of like general chemistry 251 type of lecture material right here. All right. So that is there. That takes place, and that is a carboxylic acid reaction. And I don't want you to forget that, even though that this lecture module and even your textbook, if you're following along, it really doesn't drive home that concept. Now, another set of reactions that we can also talk about with a carboxylic acid. Again, they're not really going to talk about it too much, but they're out there, and they can happen. And I at least want to mention it. Right? I mean, I'm doing you an injustice if I don't. So this is a carboxylic acid. I know that. You know that. But look at this. This is an OH group. Well, that OH group could be regarded kind of like an alcohol group. And how do we start off this semester? We started it off by talking about alcohols and alcohol reactions. And we said alcohols are very stubborn. They're not going to want to do anything that you want them to do. They're going to kind of fight back a little bit and say, no, I'm not going to react. Well, there is a way that we can get that alcohol to react. Do you remember what we did with it? Can you dig back into that filing cabinet? Can you pull out those reactions? One of the ways that we were able to get an alcohol to react is if we protonate it. So if we add some type of acid, and that acid could come onto this OH group and protonate that OH group, then folks, here we go. This is a very good leaving group. And we can do that in this world of carboxylic acids. We can do it. So if you see a carboxylic acid reaction, and they're adding an acid to that reaction, then all of a sudden, we can actually get this reaction to go forward. So protonation of the alcohol basically comes back. It's that same mechanism and it's that same template. So these are kind of the two side reactions that I just want you to go back and keep in mind. We can react them with a base. We can also protonate the OH group, and we can get that OH group to leave because of that. So here's an example. Let's take a carboxylic acid, and we'll just keep it simple. I'll put a CH3 over on this side. And then we're going to react this with CH3OH, and then on the arrow, I'm going to put H+. That H+ can come from a strong acid. So this would be something like HCl maybe, right? So that H+ is my protonation source. It is my hydrogen source. This is a catalyst that makes the reaction go forward. As always, in Chemistry 251 especially, we talked about these alcohols, and I said, listen, the alcohol can actually protonate too, and we can get this split that happens here, just like H and OH. So we broke a double bond, we added H on one side, OH on the other. We broke a double bond, we added H on one side and OCH3 on the other. So the same thing can happen here. If we put this into an acidified environment, the acid will first land on top of this oxygen to create a protonated alcohol group. And this protonated alcohol group, folks, if you go back and take a look at the nucleophilicity chart, is pretty ugly. It is a very good leaving group. So what happens here is that the OH comes in with its negative charge because it's the nucleophile, and it sees, ooh, an acyl carbon. And that acyl carbon shifts those electrons up, and oxygen says, oh, no, 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 you get these electrons back. And then carbon says, oh, no, what am I going to do? And then that carbon basically says, protonated alcohol, you got to go. Bye-bye. And then away that water molecule goes. So what we have left here is a substitution reaction. It is an acyl substitution reaction. The creation of the double bond O still is at play, and what we have here is an OCH3 at this point, and then water is spit off as a byproduct as well. So we can go through and we can name these just like before. Here's a carboxylic acid. This is a 2-carbon carboxylic acid. So we can call this an ethane, drop the E and add oic acid, so ethanoic acid. Or the common name here for a 2-carbon chain is acete. And instead of oic, I can just add IC. So acetic acid is also this molecule's name. So acetic acid can react with methanol or methyl alcohol, you pick, in the presence of an acid catalyst, such as hydrochloric acid, to create basically an ester and water as a product. Now, we can go through and we can name that ester as well, just like we did the carboxylic acid. It's a good review for us. So the CH3 group is what's connected to the O. So we name that first, and that's a methyl group. And this is a 2-carbon long chain, which is ethane, drop the E, and with these endings, they get OHs. So methyl ethanoate, or common name, I can do methyl, and then 2 carbons is acete, and then I can put 8 at the end. Again, drop the O off. So methyl acetate. So acetic acid reacts with methyl alcohol in the presence of an acid in order to form methyl acetate and water as a product. So that's how those reactions go forward. That's kind of how the mechanism takes place. So protonation, pretty important. It does take place. Here's an example of it. We can protonate that alcohol group just like we did in the very first module of the semester, and these reactions go forward just as planned. All right. So sometimes this carboxylic acid reaction is called a Fissure Esterification, and the reason it's called an esterification is because, look, we're making an ester. So Fissure, of course, was the last name of the guy that kind of reported this the very first time. So Fissure esterification. Taking a carboxylic acid, adding an alcohol, and we get a ester. This is great, by the way, for the cosmetic industry. And the reason that I say that is because here we can take carboxylic acids like vinegar, and I can take alcohols and I can change the alcohols up. I can change the carboxylic acids up, and I can end up getting different types of esters that we can make in a laboratory. And again, these esters are smell good molecules. So this is the way that I can make artificial scents. So these are our cherries and our pineapples and our bananas. Everything that could go into lotions or shampoos or conditioners or colognes. So all of this stuff is ester based, and I can make any of those scents that I want to if I end up with an ester. And the easiest way to do that in a laboratory is to throw some carboxylic acid in, throw some alcohol in, and mix these two things up, folks. Sometimes heat isn't even needed either. I just need to mix them together, give them a swirl, let them sit out for a few minutes, like 30 minutes or so, and then go back and take a sniff. And you will end up with some pretty smell good compounds on your hands. All right. Okay, so that's a little bit about carboxylic acids. Now, what about amides, the NH2 group? Can we form an amide here? All right, so C double bond O, OH, and then a random methyl group or ethyl group or ring group on the left-hand side, and we react this with NH2. All right, so if you look at this reaction, you're going to say, well, yeah, something can happen here, right? Because NH2 is Miss America, NH2 is at the bottom of the list, and NH2 is the bully and kind of basically walk into a bar and have anyone that he or she wants out of the bar. So NH2 is going to look over here and it's going to go, hey, hubba hubba, and this is an acyl group, and that carbon's absolutely, and then it will kick off an OH group, right? Well, no, not necessarily. That's not really how these work, because if you take a look at this setup, you're thinking the right way, because that's really how our template has been this entire time. But there's more of a basic type of reaction that happens here, because this C double bond OOH again is a carboxylic acid, And the NH2s are very good bases. And this really goes back to the traditional acid base type of molecule here. So what begins to happen is that the base will rip the proton off of the molecule instead of reacting with the molecule. So let me give you a real example using something down below. Let's say that we had CH3, C double bond OOH, and we reacted this with CH3, CH2, NH2. And this goes forward. Now, that doesn't carry a negative charge, but it's okay. It really does the same thing. I take a look at this particular setup. This is an acid and a base. So I know that you want to gravitate and put that nitrogen onto that carbon and kick off that OH group, but this is more basic than that. Not really a substitution reaction is going to happen. An acid-base reaction is going to happen. So what we end up with is the acid donating the proton like an acid is supposed to do. And this base accepts the proton just like a base is supposed to do. So we have an NH3 now, and that NH3 is going to carry with it a positive charge. So these are the reactions that a carboxylic acid will do. Not too many things beat it out. So we can protonate it to make it ugly in order for it to leave. And the one thing that does beat it out is an NH2 group. But when we bring that into the picture, we actually see that an acid-base reaction goes forward and not one of these substitution reactions that we've been seeing this entire lecture module. All right. So what are these typical things called? This is an ammonium salt. And the reason they call it a salt is because there's a positive and a negative piece that my product has formed. So in other words, NaCl, that is a salt because they're held together by ionic charges, a positive and a negative. And these two things are held together very similarly. So an ammonium salt is what these are, and that is a carboxyl group. So we can actually term this an ammonium carboxylate salt if we want it to be proper with it. So these are the products for the reaction. The organic really doesn't change. It's still there. Nothing heavily gets modified except the transfer of a proton, and that's about it. All right. So this basically setup will happen every single time that we add any kind of carboxylic acid and any type of amine to this particular molecule or to this reaction, all right? Now, that leads us into the last set of reactions that we want to talk about, and these are our amides, so our NH2 groups. So our amides are our carbon double bond O with a NH2 that happens at the very end. So you're looking at this molecule, and I hope that you're thinking, when you look at this molecule, well, wait a minute, that's an NH2. That NH2 is at the bottom of the list, and nothing really else was below the list. So does that mean that no reactions happen? Well, of course not. That's not what that means. That would be too easy. So here, I'm going to say that these are very stubborn, which means that if you are only going by that chart, that NH2 group is at the very bottom. That NH2 group cannot be replaced that well by any of those other groups that's on the chart. So if we only go by that, and that is it, then the answer is yeah, there's no reactions that can go forward. But we can get these to be reactive. How do we do that? Well, we're going to add in a little bit of acid and a little bit of heat. That is what these reactions are going to require. And if we add acid and if we add heat, then the rules kind of change up on us a little bit. We can get these things to react and to do something. So let me kind of show you how this happens. Let's say that we've got a CH3 group, a carbon double bond O with a NH2. All right, we'll just keep it like that. Very simple. And now let's add water and acid with some heat. what would happen here? Well, if I just do water and NH2, nothing goes on, folks. Because here I'm relying on my H and my OH to split up, and this OH is an uglier type of group than the NH2 group is. So if this OH comes in, attacks the carbonyl, carbonyl shoves up, oxygen shoves them back down, carbon makes a decision on which one to keep, it's going to look at that OH and it's going to go, sorry, try another day. And it just shoves that OH off. It's not going to accept the OH as the new incoming group, and that's because it is a better leaving group. It is an uglier group. It's a weaker base than that NH2 group is. All right, so no reaction is going to happen if it's just water. But if I throw proton into the mix, then that does change up things a little bit. Well, how? What happens? Well, if I put this in an acid environment, this acid, oh, I see where this is going. This is an acid. This is a base. Because that NH2 group has a free set of electrons on it that could accept a proton, just like the definition has always been there. So if I throw in H+, it does very similar things that an OH group would do. We can protonate the amine group. So that hydrogen can basically sit on top of that nitrogen and create a positive charge. Now this is something completely different. This is a protonated amine. And a protonated amine, folks, is a much uglier leaving group. I mean, we've just punched that in the face and gave it a black eye. Nobody wants it no more until it gets better. So the hydrogen will protonate the amine group. That protonated amine group will end up leaving if a better nucleophile can come into the picture. So now OH sees its opportunity. OH can come in and say, hey, carbon, hubba hubba, you want to go? And that carbon basically says, well, let me see here, I've got to think. So shove the electrons up, shove the electrons back down. Now we get these groups that come along for the ride. The NH2 is now an NH3 that is positive. This OH group has brought along that hydrogen initially, but as with all the other times before, it ends up removing that hydrogen to become a neutral charge. And now this carbon has a choice. And the choice is a protonated amine or an alcohol group. And the protonated amine is further up on the chart, which means that it's an uglier group, and OH will beat it out. So carbon does, in this case, decide to cleave that bond, away it goes, and then this nitrogen becomes very happy, because now what it does is it forms an NH3, which is ammonia, and no longer is it positive charge anymore. It's just lost that extra bond that was there that was causing the problem. So we get this generation of a carboxylic acid, and then we end up getting this NH nitrogen containing compound as well. So that basically is what goes on here, folks. I could take this another step forward, and typically what happens here is that, remember I told you that this O group spits off a hydrogen? Well, this is a proton, and this is still a base. So these two things can actually end up reacting together, and this could form another positive ammonium type of compound, which is okay. I mean, yeah, it's positive, it's not neutral, but folks, if anything's going to carry a positive charge like this, it's going to be a very good base, and that's going to be something like a nitrogen-containing compound. So these are very common for us to see. So a reaction can go forward with the amides, even though the amide group is the lowest on the list and nothing can really beat it out. We can give it black eyes and bust it up a little bit, and we do that with a proton. We protonate it just like we do with the OH group. All right? Okay, so let's do one more example of those just to kind of hit the point home, and this will be our last example. Can you believe it? Maybe our last example of the lecture series with our first type of carbonyls. It's almost over, but we still got a long way to go. Oh gosh. All right. So here's a amide, and let's take a look at this alcohol. Goodness gracious, what did I end up writing? So let me erase this. CH3CH2OH. And we're going to add a little bit of acid and some heat into this reaction. All right, so normally you would look at this alcohol group, you would split that hydrogen off, and you would go, oh, the OCH2CH3 is going to go onto this molecule, and it's going to substitute it off. But the problem is that OCH2CH3 is uglier than the NHCH3. All right, and because of that, no reaction is going to go forward unless we protonate it first. So that's the purpose of the acid. So once more, if this acid is not there, you are going to write no reaction. All right, if the acid is not present, no reaction goes on. That amide will not react with that alcohol because the alcohol incoming group is going to be a worse leaving group than that NHCH3, all right, or a better leaving group. So it just gets kicked back off. Now, if I add the acid on, just like we did before, it protonates that piece. That piece now becomes a very good leaving group. So we will eventually add on the OCH2CH3, and we'll cleave that bond off. And folks, there it goes. So I'm just going to erase this entire piece so we don't get confused. And there is the major organic product that forms at that point. So we have ended up forming a C double bond OO, and that is a ester in this case. So an ester has been formed. Now, I can go through and I can write in the nitrogen-containing piece. So that nitrogen-containing piece was the N and the H and the CH3. So we've gained a proton from the initial stage. So that's an NH2CH3. However, this oxygen also had a proton that it spit off. That proton's now freed up in solution, and this is a base. And that proton can actually go to that base and form an NH3, which is a positive charge. So again, that's perfectly okay, but that's where those two protons are coming from. One's kind of coming from the acid, the other one's kind of coming from the other hydrogen that's getting spit off from that alcohol group. All right? Okay, so that's it. No more reactions that we are going to talk about in this part of the lecture module. I think this is enough. So you go through and you take a look at the carbonyl types of functional groups that we've discussed. There's quite a few of them. We went through and talked about the different ways that they react, and it's all based on the same type of template, and it's all an acyl substitution reaction. No matter what we have, an acyl substitution reaction. The only little monkey wrenches that I'm throwing in are the traditional acid-base reactions that happen toward the very end. And that's because these molecules are somewhat stubborn. They do not have very good leaving groups. So protonating the alcohol of a carboxylic acid makes it reactive. Protonating the amide to make a very good leaving group with the protonated amine, that makes it very reactive. And that's one of the ways that we can get these things to participate in a reaction for us. All right, so that's it. That's all that I need to say about this part of the carbonyl. We do have a second part of a carbonyl, and we're going to focus on the other types of functional groups that can happen because there's more of them, but not as many in the second round of carbonyls. All right, so that's what we'll talk about next in the other part of this lecture module or the next lecture module that you'll experience. All right, so good luck on the online assignments. That's where this information will stop, and I'll see you in the next one.